85 kilometers. That is nothing. A short Sunday drive, a commute, 40 minutes on a flat highway. But this highway is not flat. It drops 2,140 meters in elevation. It crosses one of the most geologically unstable sections of the Andes. And for millions of Colombians, it is the only road connecting their capital city to an entire half of their country. Zero alternatives. Welcome back to the channel. Today we are talking about one of the most extraordinary and punishing road engineering projects in South America, the Bogotá-Villavicencio Highway, La Vía al Llano, a corridor that took 30 years to build, a corridor that has been torn apart by earthquakes, devoured by landslides, and scarred by disaster. A road where a bridge 280 meters above a gorge simply fell. A road that Colombia refused to abandon because it could not afford to. This is not just a road through a mountain. It is the only lifeline connecting the dense, cold highlands of Bogotá, Colombia's capital city of 8 million people, to the vast eastern plains that stretch all the way toward the Amazon basin. It is the artery through which fuel, food, medicine, cattle, and cargo flow into one of South America's most productive agricultural regions. Shut this road, and the Llanos Orientales, the eastern plains, begin to suffocate. In 2019, when landslides closed the corridor for weeks, regional guilds calculated economic losses of roughly 2.3 trillion Colombian pesos. One road, one corridor, one chance to get it right. And they almost didn't. Before we continue, make sure to subscribe to the channel and hit the notification bell. We cover engineering projects that the mainstream media ignores, the ones built in the places where they should never have been built. Stay with us until the end of this video, because we are going to walk you through the engineering challenge that broke several contractors, claimed lives, and ultimately forced Colombia to completely reinvent how it builds in mountains. What if I told you that this road has been under active construction in some form since 1994? That the original concession contract signed 30 years ago ended up being modified 53 times? That even the world's most advanced bridge building techniques failed here? And that the final section of the highway was only completed in July 2022. This is that story. At first, there was only a narrow colonial-era road, no tunnels, no viaducts, no dual carriageway, just a single lane carved into the face of the Cordillera Oriental, the eastern Andes, winding down through fog and cloud and vertical rock, dropping from the savanna plateau of Bogotá at 2,600 meters into the hot, humid lowlands of Villavicencio at 460 meters. The journey took 5 hours, sometimes 6. Sometimes a landslide would close the road entirely and there was simply nowhere else to go. Imagine standing at the edge of the plateau. Below you, the mountain just drops away, not gently, not gradually. The Andes here does not slope, it falls. Cliffs, ravines, river canyons, cloud forest clinging to near vertical slopes. The Rio Negro carves a canyon so deep that bridges spanning it would have to hang 28 stories above the water. The rock beneath the surface is young, geologically young. The Cordillera Oriental is one of the most recently formed mountain ranges on the planet. Still rising, still shifting, still alive with tectonic stress. Water saturates everything. Every rainy season, the hillsides move, not metaphorically. They actually move. Material, mass, rock, earth, sliding downward, consuming whatever was built on them. This was the terrain Colombia decided to modernize. If you try to blast through the rock directly, the mountain fights back. The geology beneath the surface shifts unpredictably. What looks stable from above may be a fractured mess 30 meters down. If you try to build on the slopes eventually give way. Every few years, a section of road simply disappears, swallowed by a derrumba, a collapse, a landslide that pours millions of tons of material across the carriageway in hours. If you try to build bridges over the deepest ravines, you face foundations in steeply sloping hillsides with complex underlying geology, soil, and rock that has never borne the kind of loads that a 446-meter cable-stayed viaduct demands. And if you try to avoid all of this by tunneling, you find yourself boring through fractured rock under extreme water pressure, navigating geological faults and unpredictable strata that can shift the tunnel alignment mid-construction. So the solution was not a bridge, it was not a tunnel alone, it was not a slope stabilization program by itself. It was all of those things simultaneously across 85.6 kilometers of the most technically demanding road corridor in Colombia's history, a system of systems. A machine made of concrete and steel inserted piece by piece into a living, moving, breathing mountain. 85.6 kilometers. 3 sections, tercios, managed by multiple concessionaires, spanning 3 decades of construction effort, divided into phases, contracts, legal frameworks, engineering revisions, disasters, and recoveries. The full corridor would eventually include approximately 28 tunnels totaling more than 30 kilometers of underground passage and more than 140 bridges and viaducts carrying the road over ravines, rivers, canyons, and drops that no vehicle could otherwise cross. Let us start at the beginning. The story starts in 1993. During the government of President Cesar Gaviria, Colombia's Planning Council, the COMPES, authorized the construction and modernization of the Bogotá-Villavicencio highway corridor. The following year, in August 1994, the Instituto Nacional de Vías, the National Roads Authority, awarded the concession, Contract 444 of 1994. The winning company, Concessionaria Vial de los Andes, known as Coviandes. The mandate: study, design, build, operate, and maintain the highway under a public-private concession arrangement. The original contract value, over 79 billion Colombian pesos. The original concession period, 16 years. It sounded straightforward. It was not. The problem began immediately. Coviandes signed the contract without having definitive final designs. The highway existed on paper as a concept, a general alignment, a political commitment, but the exact engineering had not been resolved. This was not unusual in Latin America's infrastructure concessions of that era. What followed was predictable. As the design work progressed and the actual conditions of the terrain became clearer, the scope, the cost, and the timeline all expanded. Over the life of Contract 444, the agreement was modified 53 times, 53 formal modifications, each one adjusting the scope, the timelines, the obligations, the costs. The mountain was teaching the engineers what it would and would not allow. Then came the surveys. The corridor was divided into sections for methodical study. Geotechnical teams descended into the ravines of the Rio Negro Canyon, the river that runs alongside much of the route. They drilled cores, they analyzed soil profiles, they mapped the fault lines. They identified what engineers call puntos críticos, critical points, sections of the existing road that were sitting on unstable ground, places where the mountain had already failed once and was likely to fail again. The data was sobering. The Cordillera Oriental here was not a simple, solid block of stone. It was a mosaic, fractured schists and shales, layers of sediment deposited in geological epochs long before the range was thrust upward, now tilted, cracked, saturated with groundwater, and prone to movement under load. Every meter mattered. The geotechnical reports told the construction teams something important. You cannot simply build on what is here. You have to stabilize it first. Before a single lane of new carriageway could be laid, the existing ground had to be treated, drained, anchored, reinforced, shored up with retaining walls and slope protection systems and drainage networks designed to intercept rainwater before it could saturate the slopes and trigger collapse. This work was invisible. No ribbon cuttings, no presidential visits, just teams of workers on near vertical hillsides, installing drainage channels, rock bowls, shotcrete facings, gabion walls, and earth anchors, a vocabulary of slope stabilization that most travelers who use the road will never know. The second section of the highway, the middle 29 kilometers running from El Tablón to the zone known as Chirajara, was where the most spectacular engineering would eventually take place. This section traverses the deepest and most dramatic part of the Rio Negro Canyon. Here the road does not merely descend, it plunges through a landscape of vertical walls and narrow gorges where the only way forward is to cross over void after void after void. The construction plan for this second tercio was extraordinary. 45 bridges, 18 tunnels, 4 escape galleries, secondary tunnels running parallel to the main tunnel bores, provided as emergency evacuation routes if something went wrong inside. Think about that, 45 bridges in 29 kilometers. That is more than 1.5 bridges per kilometer on average. Some of them are large, some of them are massive. Every bridge meant foundations drilled into a hillside that may or may not hold them. Every bridge meant concrete poured in conditions that tested the limits of the equipment available. The tunnels were their own category of challenge. Tunneling through the Cordillera Oriental here was not like tunneling through granite. This was sedimentary rock, shales, siltstones, fractured mudstones, with unpredictable water infiltration, variable rock quality, and a tendency to close in on the excavation face if support was not installed immediately. The tunneling crews used the new Austrian tunneling method, a system that installs support as excavation progresses rather than waiting until a full section is complete. Workers drilled and blasted in carefully controlled rounds, installed steel ribs and shotcrete immediately, applied rock bolts to stabilize the crown and walls, and advanced meter by meter through rock that frequently surprised them. The pace was governed entirely by the mountain's cooperation. On good days, solid rock, minimal water, a tunnel face could advance several meters. On bad days, the face would encounter a fractured zone or a water-bearing fault, and progress would slow to nothing while engineers reevaluated and redesigned the support system. Every tunnel required advanced drilling to probe ahead of the face, installation of drainage systems to relieve groundwater pressure, systematic rock bolting of the crown and sides, shotcrete application, steel arch ribs where the rock was too weak to stand on its own, invert concrete to seal the base, and finally the finished concrete lining. All of this in confined spaces, in high humidity, in noise and dust and heat, often with limited access. Because these were not tunnels built from a flat urban site, these were tunnels built on the side of a mountain, reached by access roads that were themselves constantly at risk from the same landslides that threatened the main corridor. Every worker mattered, every bolt mattered, every pour of shotcrete mattered. Then came the bridges. Then came the bridges. And no bridge on this entire corridor would come to define the project, its ambition, its vulnerability, and ultimately its tragedy, more than the one at Chirajara. The Chirajara Gorge is not a gap you can simply ignore. It is a void, a vertical cut in the mountain so deep and so steep that no approach road could descend into it and climb back out at any viable gradient. The canyon drops roughly 280 meters from rim to river. You cannot go around it without adding many kilometers and an entirely new alignment. You cannot go under it. The depth of the void makes a tunnel impractical at this location. The only option is to go over it, and going over it means a bridge of a scale that tests the outer limits of what Colombian engineering had attempted at the time. The design chosen was a cable-stayed bridge. The form is elegant in principle. Two towers rise from foundations on either rim, and from those towers, steel cables fan outward in a harp or fan pattern to support the deck below. The deck hangs from the cables. The cables transfer the load to the towers. The towers push the load into their foundations. It is a chain of dependencies as precise and interconnected as any mechanism in engineering. The tower needs the cables need the deck needs the cables need the tower, and the tower needs the ground. At Chirajara, the bridge would span 446 meters in total, with a main span of approximately 286 meters. The towers, two of them, rising from the edges of the gorge, were designed in a diamond shape, not the simple rectangular mass you see on many cable-stayed bridges. A diamond, two legs converging at the bottom into a foundation, spreading wide at mid-height, then converging again at the top where the cables attach. Elegant, innovative, and, as it would turn out, fatally flawed. The structure was built with a main span of 940 feet, around 286 meters, and two side spans of 262 feet. The deck would carry traffic across the gorge, connecting a tunnel mouth on the Bogotá side to another tunnel on the Villavicencio side. The bridge was scheduled to open in March 2018. By January of that year, the construction was close to complete. The deck sections were advancing toward each other from both towers. Almost everything was in place. There were, according to reports at the time, approximately 200 workers assigned to the site. And then, on January 15, 2018, at approximately noon, the mountain made its answer known. With only 164 feet of the floor system remaining to be constructed between the two advancing deck sections, the western tower suddenly collapsed, with little to no warning, resulting in complete failure of that portion of the bridge superstructure. The deck section on the Bogotá side, hanging from cables attached to the collapsing tower, fell with it. Hundreds of tons of concrete and steel dropped into the gorge below. 10 workers lost their lives. 9 died at the site of the accident, and 1 was transferred to a hospital where he later died. Workers plummeted an estimated 280 meters. The number could have been catastrophically higher. The death toll would have been much higher if 180 other workers who would have been on the structure had not been attending a training session on the opposite side of the ravine. A coincidence, a scheduling quirk. A training session that nobody planned to coincide with a structural failure, and that saved the majority of the workforce. The eastern tower, the one on the Villavicencio side, remained standing, damaged, compromised, but standing. The road closed. Coviandes activated an emergency security plan. The National Agency of Infrastructure, the ANI, convened emergency meetings and then began the long, painful work of understanding what had gone wrong. The investigation was assigned to the American firm Modjeski and Masters. Their work was methodical: site inspection by drone and on foot, structural analysis, review of all construction documentation, interviews with the project team, materials testing from recovered components. They had approximately 50 weeks of wreckage and data to examine before the report was published in April 2018. The report concluded that the collapse of Tower B, the West Pier, was due to a design error, with an incorrect assumption made about the strength provided by transverse tie beams and a diaphragm at the diamond-shaped pier. The report ruled out suggestions that the accident was due to poor quality of materials. The horizontal connection within the diamond-shaped towers was insufficiently designed with a minimal number of pre-stressing cables. Incorrect calculations had also been made about the lateral strength of the concrete diaphragm wall connecting the lower V-shaped legs of the towers. This is not a small oversight. This is not a question of one bolt being the wrong size or one batch of concrete being slightly weaker than specified. This was a fundamental error in the structural logic of the tower itself. The cross-tie, the element connecting the two spreading legs of the diamond at their widest point, where the outward thrust of the legs generates the greatest lateral tension, was simply not strong enough to hold them together under the full load of construction. It was, according to the investigation, only 0.6 meters thick, with just one row of 12 pre-stressing cables, far thinner and less reinforced than is typical for this kind of bridge tower, where such beams are normally at least 2 meters thick with several rows of pre-stressing cables. The mountain had not failed, the geology had not shifted, the cables had not snapped. The error was on the drawing board years before the first cubic meter of concrete was poured, and it took the collapse of a nearly complete bridge and the deaths of 10 men to reveal it. The report also found cracking on Tower C, the eastern tower, which remained standing, consistent with the early stages of the same collapse mechanism, and recommended its demolition. The eastern tower was already failing by the same logic. If the western tower had somehow held for one more week, the eastern tower might have gone next. So both towers had to come down. The entire structure, years of work, millions of pesos of material, everything that had been built on that gorge had to be removed and the process begun again. In July 2018, the controlled explosion brought down the remainder of the deck and the standing support tower. The charge used approximately 200 kilograms of explosive. Detonating cord, charges set at key structural points, the calculation of which direction several hundred tons of concrete would fall into a gorge 280 meters deep. The explosion lasted seconds. What it destroyed had taken years to build. The Colombian government made its position clear. The state would not pay for the replacement. The government expected Coviandes and its insurance cover to bear the cost of rebuilding. The bridge had failed due to a design error. The responsibility was private. Then came the rebuild. In October 2018, the new contract was awarded. The consortium, Eiffage Génie Civil, and the group's Colombian subsidiary, Puentes y Torrones. French engineering now applied to a Colombian gorge. The brief was clear: design and build a new cable-stayed bridge at the same location. Learn from what happened, do not repeat it. The new design was not a diamond. The new structure would be supported by two V-shaped piers, a fundamentally different geometry from the diamond that had failed, rising to a height of 150 meters above the ravine, with a main span of 286 meters and a total length of 446 meters. The V-shape works with a natural flow of forces rather than against it. The legs spread at the base, where they connect to the foundations, and converge at the top, where the cables attach. The lateral thrust that destroyed the first bridge becomes, in the new design, a compression force that the concrete can handle more cleanly. The geometry is different. The structural language is different. The investigation had found that the original foundations were structurally and geotechnically adequate and could be retained for the reconstruction. The ground was not the problem. The ground could be reused. The new towers would be built on the same caissons sunk into the gorge walls by the original crew. The earth would hold. It was the design above the earth that had to change. The project involved 4 months of preliminary studies and approximately 18.5 months of construction work at a budget of around $21.5 million US. This was not simply a matter of building the same thing better. It was a matter of rebuilding trust. Trust in the engineering, trust in the concession, trust in Colombia's capacity to finish what it starts, even when the mountain and its own institutions push back. Imagine the crews that return to that site. Imagine descending again into the Chirajara Gorge, now littered with debris from the structure that had killed their colleagues. Imagine setting up the construction platform again, rigging the cranes again, laying out the formwork for new tower legs, pouring concrete in the same vertical air above the same canyon, with the memory of January 15 present in every shift. Every bolt mattered even more now. Every calculation mattered more. Every weld, every cable anchor, every pour of concrete carried the weight of what had come before. This was not just construction. This was redemption through engineering. Meanwhile, on the rest of the corridor, work had never fully stopped. The disaster at Chirajara was the most visible rupture in the project's history. But the 70-odd kilometers of the highway that lay outside that gorge continued to advance, section by section, structure by structure, through the fog and rain of the Cordillera Oriental. The tunnel network deserves its own account. By the time the corridor was approaching completion, Indra, the Spanish technology company serving as Coviande's principal technology partner, was managing the intelligent systems installed across the route. Indra was responsible for installing intelligent traffic, control, and communication systems for 18 tunnels and 47 bridges carrying more than 10,000 vehicles a day on the Bogotá-Villavicencio highway. 18 tunnels. Consider what that means operationally. Each tunnel is its own contained environment. Once a vehicle enters a tunnel portal, it is inside a sealed space. No natural ventilation, no natural light, no direct communication with the outside world. In a short tunnel, 200, 300 meters, this is a manageable inconvenience. In a tunnel that runs for several kilometers, it becomes a controlled environment that requires active management. Ventilation fans to maintain air quality, lighting calibrated to prevent the pupil adjustment problems that cause accidents at exits, drainage systems to prevent water accumulation on the roadway, fire detection sensors positioned at intervals, CO and pollutant monitoring systems, variable message signs to alert drivers to conditions ahead, cameras feeding a live picture to a control center, emergency telephones at regular intervals, and, critically, escape galleries. The escape galleries are the elements that most drivers never notice. They run parallel to the main tunnel bore, connected to it by cross passages every few hundred meters. If a vehicle fire occurs inside the main tunnel, the escape gallery gives people a refuge, a separate smoke-free passage through which they can walk to a portal or an emergency exit. Without it, a fire inside a long tunnel is a catastrophe. With it, a fire becomes a survivable emergency. One of the tunnels on the corridor, located between Guayabetal and Puente Quetame, reached 4.4 kilometers in length, the fourth longest road tunnel in Latin America at the time of its opening. This is the Renacer Tunnel. To build it required boring through kilometers of the Caqueza Formation, the same sedimentary sequence of lutites and siltstones and sandstones that tunneling crews encountered throughout the corridor. The Caqueza Formation is not cooperative geology. It is layered, fractured, water-bearing in places, and apt to move. The tunneling crews used every tool available, probe drilling ahead of the face to identify water-bearing zones before hitting them, pre-grouting to seal water inflows before excavation, careful blast sequencing to minimize disturbance to the surrounding rock mass, immediate support installation after each advance. The three tunnels of Sector 1, La Herradura at 299 meters, Moscosio at 384 meters, and La Culebra at 539 meters, all traverse rock mass in the lower Caqueza Formation, made up of lutites with interspersed layers of siltstone and sandstone. These were not headline structures. They were working tunnels, built in the early sections of the corridor, bored through rock that refused to behave predictably. And yet they function every day, every hour. Every vehicle that passes through them is, without knowing it, benefiting from a decade of accumulated learning about how this particular mountain yields and how it holds. The Indra Horus system was installed on the Herradura, Moscosio, Culebra, and Oro Perdido tunnels, designed to facilitate operation, automate processes, reduce the risk of incidents, streamline management, and provide safety for drivers. This is the invisible nervous system of the highway. The drivers who pass through these tunnels see smooth concrete walls and overhead lights and the yellow glow of sodium lamps. They do not see the sensor arrays reading air quality 24 hours a day. They do not see the ventilation logic adjusting fan speed in response to detected CO concentrations. They do not see the cameras tracking every vehicle, logging entry times, and flagging vehicles that stop in prohibited zones. They do not see the control room operators watching every tunnel on a single screen, ready to close a portal and activate emergency protocols in less than a minute. This was not just a road, it was a living infrastructure system, and it had to be kept alive even as parts of it were still being built. The third section of the corridor, from the area around Chirajara and Guayabetal down toward Villavicencio, brought its own set of complications. As the highway descends from the high Andean slopes into the transition zone where the mountains begin giving way to the plains, the terrain changes character again. The slope angles ease slightly, the rainfall increases, the vegetation thickens, and the geological conditions shift towards softer, more erodible material. Alluvial fans, terrace deposits, colluvial slopes built up from thousands of years of material slowly washing down the mountain face. Building in this zone requires the same discipline as the higher sections. Drainage above all, foundation quality above all, slope stabilization above all, but the mechanisms of failure are different. The threat here is not deep-seated landslides triggered by fault reactivation. It is surface erosion. It is shallow slope failure. It is the slow, relentless creep of material downhill when rainwater is not intercepted and redirected by a designed drainage system. The drainage network on this highway is a feat in itself. Hundreds of culverts carry water under the carriageway. Roadside channels intercept runoff from the slopes above and direct it into concrete flumes that guide it down to the river systems below. Lined ditches prevent water from infiltrating the subgrade under the road surface. Interceptor trenches cut across the slope above the road prism, capturing groundwater before it can saturate the fill below. Energy dissipators, structures that slow fast-moving water and prevent it from eroding the channel floor, are placed at every point where drainage changes gradient. None of this is visible from a moving vehicle. All of it is the reason the road is still there. Every drainage element mattered. Every culvert mattered. Every interceptor trench mattered. The years between 2018 and 2022 were years of rebuilding in every sense. The Chirajara Bridge was being redesigned and reconstructed under the Eiffage Consortium. The remaining structures of the second tercio were being completed. The slope stabilization works that were always in progress, that never truly stop on a corridor through the Andes, continued. And the last sections, the pieces that closed the gaps in the dual carriageway alignment, were being pushed toward completion. The section of highway between Puente Cuaitam and Naranjal, incorporating 10 tunnels, opened in 2015. The Renacer Tunnel opened in 2016. The section incorporating the Herradura, Moscocio, Culebra, and Oro Perdido tunnels was opened in November 2017, just 2 months before Chirajara fell. And then the collapse froze the project's momentum for months, directing attention, resources, and national anxiety toward a single gorge in the middle of the corridor. But Colombia did not stop. It never fully stopped. And in July 2022, 28 years after Contract 444 was signed, the corridor was declared substantially complete. 28 years, more than half a century of Colombian political cycles, multiple concession modifications, the collapse and complete reconstruction of its most spectacular bridge, landslides that closed the road for weeks at a time, a construction site that was never, not once, free from the threat of the geology it was embedded in. Most people who drive the Bogotá-Villavicencio highway today experience the journey in something under 2 hours. They descend through tunnels so smooth and well-lit that the mountain seems almost cooperative. They cross viaducts over gorges that, a generation ago, were simply void, impassable, ignored, left to the condors. They look out through the windscreen at the green walls of the Cordillera Oriental and perhaps they think, what a beautiful drive. They do not see the geotechnical engineers who spent years mapping fractures and faults before a single machine moved. They do not see the tunneling crews who worked in darkness and heat and noise, advancing meter by meter through a mountain that did not want to be bored. They do not see the bridge workers who came back to the Chirajara site after January 2018, who strapped on their harnesses and leaned out over a 280-meter gorge and picked up where the previous crew had left off. They do not see the drainage engineers who designed the invisible water systems that hold the slopes in place through every rainy season, year after year. They do not see the control room operators who watch every tunnel through the night, managing an infrastructure system that never sleeps. They do not see the contract negotiators who fought through 53 modifications to keep the concession viable and the work moving. They do not see the families of the 10 men who fell from Chirajara on a Tuesday in January, who lost someone so that the road would eventually be built, and built correctly. This was not just a road. It was a 30-year conversation between human ambition and a living mountain. and neither side entirely won. The mountain took 10 lives and broke a bridge and disrupted the journey of a nation. The humans took 30 years and 53 contract modifications and the stubborn refusal to abandon the project and cut a corridor through the Andes that now carries medicine and fuel and cattle and children from the capital to the plains and back again, every hour, every day, every year. Every driver on that road is the beneficiary of a generation's worth of engineering courage. Without it, a region suffocates. With it, a country breathes. If you found this story worth watching, subscribe to the channel and leave a comment below. What engineering project should we cover next? Every click, every subscription, every comment is what allows us to keep covering the projects the world overlooks. Thank you for watching.